So today we're going to talk about tokenization in natural language processing. Basically, what tokenization is how we make text machine readable, right? So have you ever wondered how a computer model like ChatGPT understand human language? Machine can't see words the way we do. They only understand numbers. The bridge between our messy, expressive language and a model's precise mathematical word is a process called tokenization. Humans use natural languages like English, Arabic, Portuguese, or Mandarin. Computers, in contrast, rely on machine languages, which are basically formal, rule bound systems such as C or Python, or even lower level languages like assembly or 8051 or Lisp. When we ask an AI model to summarize an article or translate a sentence, the first step is to convert our words into a numerical form the model can process. That conversion happens through natural language processing or NLP, a field combining linguistics, computer science, and AI. Within NLP, the first essential step of nearly every pipeline is tokenization. Um, what is tokenization? Tokenization is the act of breaking text into smaller pieces called tokens, the atomic building blocks of language for a model. Depending on the method, a token could be a word, a subword, part of a word, or even a single character. Um, for instance, in the um, in the sentence, like the quick brown fox jumps over the lazy dog, it can become the quick brown fox jumps over the lazy dog. Each element is a token. Once tokenized, each token can be turned into a unique numerical ID or embedded as a multi-dimensional vector representing meaning and context. So now the question is, why does tokenization even matter? The different tokenization methods drastically affect how well a model understands language. If the tokenization is too coarse, like if the entire word is considered a token, and the model struggles with rare words, and if it's too fine, like individual letters and characters, it loses meanings. So there's a balance between the two, which is a subword tokenization, which strikes a balance, allowing models to represent both frequent and rare words. But there, in the pipeline, there is one step before tokenization, which is called the standardization. We must standardize text, which basically entails cleaning and normalizing the text so the trivial differences don't confuse the algorithm. That's basically the reason behind it. So let's take a look at these two sentences. Dusk fell. I was gazing at the Sao Paulo skyline. Isn't urban life vibrant? So these two sentences right here. And the second sentence is dusk fell. I gaze at the Sao Paulo skyline. Isn't life vibrant? So there's minor differences. I was gazing. I gazed at lowercase, uppercase. There's a hat on over A in Sao, and there's two questions mark here. So they feel to this the same to us, but to computer they're completely different because of what the differences I mentioned, like capitalization, punctuation, direct text, and contractions. We can fix it by first of all, we can lowercase all letters, removing punctuations, normalizing special characters, trimming extra spaces, and here is basically the code that does all of it for me. So we do here in this line, we take the text, so we define this as standardized text function. We take the text, we lowercase everything, then what we do is normalize it by turning it into the bring it into the ASCII character standard. Then we remove punctuations, which is line 13, and then we remove extra white spaces. You can see the process. This is the original text. Then we what we do is normalize it by bring it into the ASCII, so there's no major difference here. But then we remove characters in line 13. Line 16, we remove the white spaces. So that's what happens, right? Now both sentences become pretty much the same, except there is, the only difference is